Now, is there, for example, can I use on the same lines, can I use a multiplexer to implement a arbitrary truth table? Okay. So, what is a multiplexer? We are talking of a 2 power n is to 1 mux. Okay. So, now I am going to say the following. So, let us say now I am going to redefine my standard cell library. Okay, 0, 1, 2 power n minus 1. Okay. So, I have select signals S0, S1, Sn minus 1. Okay. So, input I0, I1, I2 power n minus 1. Okay, and my output y. And I am also saying I have a simple inverter with me. No. A and y. Okay, this is my standard cell library that I am going to now use in order to implement any arbitrary Boolean function. Okay. So, let us again look at, for example, the case of, let's take the same example that we had earlier, right? We basically said the 3 input XOR gate. Okay. So, let's consider this guy. Okay, and I am going to assume here that in my standard cell library I have n equal to 3. Okay, so it's a 8:1 multiplexer that we are talking about, right? So I want to implement this function y XOR 3 is equal to this sum of minterms 1, 2, 4 and 7. Okay, again let us look at what is this multiplexer that we have, what is that signal, what does it do? Okay, let me just go back and see, by the way, A is the MSB and yeah, C is the LSB. Yeah, cool. Okay, so let us see what this multiplexer output was, by the way. Okay, mux was simply summation or OR gate actually of mk into input ik, right? K going from 0 to 2 power n minus 1. Okay, so this was for the n input case. If it's a 3:8, we are talking about k going from 0 to 7 mk ik. Okay, one of the 8 inputs, right? Now, all we have to do is for us to understand how to map this minterms onto this thing, right? So now you just look at what does this mean? Okay, it is m1 plus m2 plus m4 plus m7. Okay, so I can write this in a slightly different way, right? Whichever minterm doesn't exist in that particular truth table, I will just put the term but multiply it by 0. 0 into m0, 1 into m1 plus 1 into m2 plus 0 into m3 plus 1 into m4 plus 0 into m5, 0 into m6 plus 1 into m7. Right? Now you compare this with this expression here. Right? You just look at the equivalence of these two expressions. It's very straightforward. there are exactly 8 minterms, and the inputs ik are being decided by what the truth table actually says, right? So therefore, if you were to implement the XOR 3, okay, 1, 2, 3, 4, 5, 6, 7, 8, right? So I have this, my output y here, this is 0, 1, 2, 3, 4, 5, 6, 7. So what are we saying now? We are just saying connect M1, M2, M4, M7 to 1, right? So M1, M2, M4, M7, all these I am going to short and simply connect to VDD or logic 1, okay? On the other hand, I'll just draw it in a different color. You know, there is no thing. I'll just connect 0, 3, 5, 6, right? So 0, 3, 5 and 6 are the unused outputs, and that I will just connect to ground, okay? This is my input combination. Now for S1, S2, S2, S1, S0, I just have to map the inputs here, A, B, C. We just have to take care to ensure that the MSB, LSB is taken care of when mapping this input space ABC to the select lines of the multiplexer, right? So therefore, this is also a very straightforward implementation as far as this multiplexer, using a multiplexer to implement a logic circuit is, right? Now of course this is only to get y XOR 3, okay? Now unlike the decoder case where we got certain minterms, we could optimize the number of OR gates after that. Technically that's not doable in case of a multiplexer, right? In case of a multiplexer, because in order to do that I basically need to in order to implement another function, I basically just need another multiplexer, because I don't have access to the internal signals, by the way, okay? Remember, the multiplexer itself is a decoder driving many tri-state inverters, right? And therefore I have an issue, I don't have access to that decoder output essentially, right, for me to optimize things further. Now if I wanted to therefore implement this, right, let me just take all this off. Yes, okay. So I want to implement this function y, okay, which is basically 0, M01, M2, M3, M4, 2, 3, 4, right? So if I were to implement that, then I just do M2, M3 and 0, 1, 2, 3, 4, yes, M4. One, okay, and then I am going to now simply connect the remaining signals here, 0, 1, 5, 6, 7 to ground like this, and I will get the implementation for the signal y, okay. So like I mentioned, it's not possible to reuse any gates here or optimize the number of gates. It's just a different implementation. You basically need one multiplexer per output, right? Now if you have higher number of inputs, then yeah, for example, if you have 6 input 6 input logic function that you want to implement, then you basically need a 2 power 6 is to 1 multiplexer, and then you just connect each of those 64 inputs to either 1 or 0, and essentially the whole thing is taken care of very easily. Okay, so now I'll look at a slightly more interesting problem, right? I'm just going to look at, for example, I'm going to now consider the case where I have a 8:1 multiplexer, but I have a 4 input logic function. Okay, so let us look at that now. So I have 8:1 mux and a 4 input logic function that I want to implement using this multiplexer, right? So normally the way we would have done this, right? What would we have done? Going by our earlier discussion that we had, we would first implement a 4:1 multiplexer using the just 3:1 multiplexers first of all, right? So what would we have done? We would have said simply consider this, right? 2 multiplexers at the input, right? So this would be my input I0, I1, I7, I8, I9, I15, right? This would have been my 16:1 multiplexer, because if I want a 4 input logic state, I am now looking at 2 power 4 combinations. So I need 16:1 multiplexer. Then I can do what I just discussed in the previous case for that XOR 3 implementation, right? So then I would basically take this and then implement a 2:1 mux, using the 8:1 mux. All I have to do is ground the other inputs, right? So I will just assume that I have this case here, select lines are here, and then this is my output, right? So if I have A, B, C and D, right? This is my logic function 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. 0, 1, 1, 0, 1. Okay. So I'm going to now replace this with just ones, right? And I have a function here. Let me just pick an arbitrary Boolean function. I'm going to just say 1, 1, 0, 1, 1, 0, 0, 0, 1. Okay, let's say this is the function that I wanted to implement, right? So based on the lower 3 bits, okay, the lower 3 bits, I will either select one of the outputs. So if you look at this, this corresponds to input I0, I1, I2, all the way. This is I8, I9, all the way to I15. So all I have to do is connect each input like this to this value, right? So that's all I have to do based on, right? So I would just have to do the following. This is 0, 0, right? Exactly for I3, right? 4, 5, 6, 7, 8, right? I would say 1, 1, 0, right. So this is 3, 4, 6, 7. Okay, 3, 4, 6 and 7. Similarly, I8 onwards, I would do the following. 8, 9, 10, 8, 9, 10, sorry. 8, 9, 10, 11, sorry. Yeah. So my implementation would be the following: B, C, D, B, C, D, right? And then I would implement a 2:1 mux by making this input as the select line as A, and then I get my arbitrary output Y as needed here, right? So essentially this is nothing but just implementing a 16:1 mux using a bunch of 8:1 multiplexers. So this we have already seen, but it's just good to work out one example explicitly, and that's why I went ahead and did this. Okay, now we have a more interesting question. Okay, suppose I tell you that you are not allowed to use an other 8:1 multiplexer. You're allowed to use only one 8:1 multiplexer, and of course the standard cell logic allows you to use inverters. Let's go back and see that it has 8:1 multiplexer and any number of inverters. So you can use any number of inverters that you want, right? Or no, not even any number. I'll make the problem even more interesting. You can use one inverter and one 8:1 mux, and you have to implement this arbitrary Boolean logic Y that you see here. Okay, let's go ahead and see how we can do that. So let me get this truth table there so that I can. Right. So I'm going to take off all this now. Okay, and let us just say, let's look at the relationship between this D and Y. Okay, I'm going to write Y in terms of D. Okay, what we did in the earlier implementation was the inputs to the multiplexer were all either 0 or 1. Okay, we are either sending it to the ground or supply. Okay, but we can technically tie these things to certain inputs as well. Okay, so let us look at this. Okay, I am going to write this a little differently. So if you look at, when A, B, C is 0, 0, okay, so look at this combination. Okay, the input is A, B, C. When it is 0, 0, 0, it does not matter what the input D is. Okay, and therefore the output is just 0. Okay, so in this case my Y is just 0. It does not depend, it's a don't care case. The D input is a don't care case. It does not matter what D is. Okay, likewise look at the next case 0, 0, 1. When the input ABC is 0, 0, 1, the output Y simply follows D. In this case Y simply follows D, right? Now you look at the third case 0, 1, 0. Okay, for two cases, for when ABC is 0, 1, 0 respectively, y is simply d bar here, right? Y is just d bar. Again this case 0, 1, 1, y is independent of d and it is just 1. Likewise here 1, 0, 0, output y is just 0, okay? And this case here when it is ABC is 1, 0, 1, again y equal to d, right? Here again 1, 1, 0, 0, 1, output is just 0, right? Now so last case when the A, B, C are just 1, 1, 1, output again is 0, y equal to 0, right? Now you can see that I have to deal only with 8 such combinations, okay? Let me number the combinations. This is 0, 1, 2, 3, 4, 5, 6, 7. Okay, I have just 8 combinations and my multiplexer can now therefore be a simply 8:1 multiplexer, right? So therefore if you see this implementation, I would simply have to do this 1, 2, 3, 4, 5, 6, 7 and I will use this 8. Okay, and all I am saying now is my select lines to this multiplexer, okay, the MSB is A, B, C, okay. I am simply going to say if it is input is 0, 0, 0, then my output Y is going to be 0, okay. So this is the 0, 1, 2, 3, 4, 5, 6, 7. Okay, and remember this is the MSB and this is the LSB. Okay, so now I have, now when input ABC is 0, 0, 1, Y equal to D. When input is 0, 1, 0, that is 2, Y equal to D bar. Okay, 0, 1, 1, Y equal to 1. When 1, 0, 0, Y equal to 0. 1, 0, 1, Y equal to D. Okay, and 1, 1, 0, it is 0. Finally 1, 1, 1, Y equal to 0. This is my Y that I want. Okay, so in some sense without having to, so by the way, let me go back to the constraint that I imposed. I said we can implement with 8:1 multiplexer and one inverter. What is the inverter needed for? To generate D bar, that's all. Okay, so D bar, that's all, right? So effectively you can just, with one inverter, the D will go to certain inputs, D bar will go to other inputs and you will be essentially done with this, right? So effectively without having to build a 2 power n:1 multiplexer, right, with just 2 power with an n 2 power n minus 1 to 1 multiplexer, you can implement an n Boolean literal logic function, right? Like in this case with it was a 4 variable function we wanted to implement, we were able to implement it with an 8:1 multiplexer. The only difference is now instead of tying the inputs to just 0 or 1, we had to tie it to 0, 1, the other left input that we left out, either that directly or its complement, right? And we were able to get the whole thing sort of implement the arbitrary Boolean function very, very nicely. Okay, of course if you need to now implement a 5 variable logic function and so on and so forth, then you have to now build at least a 16:1 multiplexer, right? And then assign that inputs to either 0, 1 or the fifth input or its complement, right? That's the essential idea behind this, implementing arbitrary Boolean functions with decoders and multiplexers.